Alright guys, welcome back. We have another question from the chapter 4 of engineering mechanics, and we have the pair of 27-pound forces that are applied to the handles of the crimper tool, and we need to determine the crimping force in the jaws at point G. We're gonna assume we are in equilibrium, and we need to dismantle this tool and apply our equation that we have for equilibrium, and we should be able to find the unknown that we are looking for in here, which is the force in the jaws at point G. So we're gonna start with this handle, and I'm just gonna show the forces in here. Alright, so I tried to draw the free body diagram in here. So we're gonna have the 27 pounds force applying at this point. We have two pins at point D and E. For E, we're gonna consider two components. Since it's a pin, we need vertical and horizontal components. Let's just show our X and Y axis here. And if we look at the point C, we see that it's attached to this member, which is a two force member. So the force in this member is going to be along the line that connects these 2 points, which are C and D. So this is going to be our force CD. We can call it, let's just call it CD or FCD. And we can use our equilibrium equations for this. So let's start with maybe sum of all moments about point E counterclockwise positive as always. Let's go write down the equilibrium equations that we have. So we have sum of all forces in X equals 0, same for the Y, and we have one moment equation as well. So here I started with the moment equation because that way we can get rid of EX and EY. They don't make any moments about point E. So we should be able to find the only unknown that we have in here, which is FCD. But before that, we need to find out some information about the angles. And for finding that angle, we're going to have this right triangle in here, which can give us information about the angles. If we just call this angle maybe alpha, which is the angle that we have in here. Let's see how we can find the angles, and after that we can resolve this force into vertical and horizontal components. So we need to figure out this side first. That side is basically 0.7 plus 0.3, which is 1 inches, and for the base we also we need this little distance, which we just need to subtract this 6 inches by 5.75, which is going to be 0.25, and that should give us the angle that we are looking for. Because if you just find the tangent inverse of the opposite, which is 1 over 0.25, that should give us the angle. So let's see what we get. Tangent inverse of 1 divided by 0.25 or 4. So our angle would be 75.96 degrees. Just double check that you have your calculator set to degrees, not radian. You're gonna get the wrong answer. So let's go for our moment equation. So we have the moment of the 27. As we can see, this moment is counterclockwise, so positive. And for the distance, we basically need the distance from E, or vertical distance from E to the line of action of 27, which is basically this 6 plus this little distance, so 6 plus 0.75 inches. We have also the X and Y components of the FCD. So if we look at the X component, first of all, we can see that the moment is counterclockwise, so another positive moment. FCD times cosine of alpha would be our X component, so cosine of 75.96 degrees. And the distance would be this little distance that we have, again, vertical distance from E to the line of action. And that's going to be 0.5 inch that we have in the figure. And last one is going to be the moment of the Y component. This one is clockwise, as we can see, so we're going to have a negative moment for this one. This time we're going to get sine of 75.96 degrees. And again, vertical distance from E to the line of action. So now we are looking for again, this distance that we had, so 0.75, and this will be equal to 0, so we should be able to find FCD from this equation. So what we can do in here, we can just factor FCD for these two expressions, and this is going to be 0.75 sine of 75.96 minus 0.5 cosine of 75.96, and in the numerator we're going to have 27 times 6.75, and let's see what we get. So 27 times 6.75, so 0.75 sine of 75.96 minus 0.5 cosine of 75.96, and this is gonna give us FCD, which will be 300.50 or 0.6. Okay, now that we have FCD, we can move on to another member of this tool. So the next member, since we are looking for the force at the jaws, so we're gonna go with this one, and we figured FCD, so we're gonna have the force FCD that we know in here, and also we're gonna have the normal force that we have at the jaw. We can call this one NG, or we can just call it N. And obviously we have two forces at X. We're gonna call Fx Fy since we have a pin, but looks like if we just use our moment equation about point F, we're going to get rid of Fx Fy, and we should be able to find the only unknown that we have, which is N. So I'm just going to draw the free body diagram for that member too. So 27 pounds in here. We figured our FCD, and we figured also this angle alpha. We are looking for the normal force at point G. And we have two forces as Fx, Fy. And our moment equation would be about point F counterclockwise positive. And yeah, let's see what we have. So we're gonna have the moment of the 27 pounds. This moment is clockwise, so negative 27. We need the distance from F to, just gonna clean up the figure. So we need the distance from F to the line of action. So basically 5.75 plus 2.75. We're gonna have the moment of the FCD, which has two components. Both of them are actually making moment. So let's start with the y component about point F. It's gonna be a counterclockwise, so positive 300.6. Sine of alpha, our alpha was 75.96 degrees. And the distance from F to C, so we are looking for this distance, which is 2.75. Again, this will be our y component in here. So this is the line of action, and our distance would be this distance, which is 2.75. And the x component, if we look at the point E, we see that it's a little bit, sorry, point C, we can see that it's a little bit above the point F. So this is the x component, this is the y component. So the moment of the x component would be in this direction, so it's clockwise. And this one's going to be negative, so minus 300.6 cosine of 75.96. And if we want to find the distance, we're going to have this distance. Again, this is the line of action, this is the distance that we are interested, so that would be 0.7. And the last one is the moment of the force, and first of all the moment is in this direction, so also clockwise, so negative n, and the distance that we have. We know our N would be along this, and we have that distance, which is 1.75 inches, equals 0, and we only have one unknown in here. So basically, whatever we have in here, I'm gonna call it A, divided by 1.75. So let's just calculate this. So 27 times 5.75 plus 2.75. Here we have 300.6 times sine of 75.96 times 2.75. Oh, sorry, this has to be in the top part. I don't know why I put it in the bottom. I also missed the negative sign in here too. So plus 300.6 sine of 75.96 minus 300.6 cosine of 75.96. I also missed the 2.75 in here and 0.7 in here, and divided by 1.75. This is gonna give us the force and 297.95 pounds. And this is what the question is asking. Hope everything was clear. Let me know if you guys have any questions. You guys take care. I'll see you in the next video. Have a good one.